Thank you. Thank you everyone for joining for this talk. I am Deepa Jagyasi and I'm a research engineer. I'm working with Professor Maso. Today I will be presenting before you a secure and robust MIMO transceiver design for multicast mission critical communication. So this work has been supported by ITEL company, and it has been funded by DGA project. The work has been performed at Link's laboratory, and I myself and Masu are affiliated with Telecom Perry as well. So mission critical communication, what exactly is mission critical communication? It is all communication that is related to the safety and security of the civil society. This include critical infrastructures and the services which are associated with critical requirements, for example, by police forces, firemen, ambulance services, and also by the energy and transportation suppliers. So any critical infrastructure such as in terms of disaster management or national security or asset management, they can be the critical infrastructure, and also the event management and the multimedia services will be included in mission critical communication. So as they are specifically for the critical infrastructure, they have special needs, and they are mostly conveyed by the professional mobile radio networks. So one of the main indispensable service that should be offered by mission critical communication is a group communication. That is, the base station or the team leader should be able to communicate with a group of the users to broadcast the service and multicast the message simultaneously. So along with the group communication, the coverage is of utmost importance. Reliable communication and secure communication is the key requirements for mission critical communication. So based on that, the key requirements for mission critical communication can be summarized as: they require the secure communication, that is, we cannot compromise on the security and reliability of the overall communication link. The coverage should be wide so as to reach more and more number of group users. The priority access, that is, it should always come about commercial cellular networks, the reliability, and special services which may include the group communication. So based on this, the outline for today's talk would be: we first talk about the motivation for this design, the model, which include the transceiver model and the network model that we will be adapting for mission critical communication design, followed by the proposed transceiver design, numerical results, and hence the conclusions. So the major motivation for this work is the wireless communication is highly prone to the security threats because of its broadcast nature. So in mission critical communication, the crucial information which is handled, we cannot compromise on that sensitive information. Hence, the security is utmost important. The goal in this work is designing a multi-base station, multi-antenna transceivers for mission critical communication that are robust to the channel state information, hence providing the reliability requirement, and the security is incorporated in the presence of multiple passive eavesdroppers. Specifically, we incorporate physical air security in two major aspects, that is, by doing the MIMO beamforming and also by adding the artificial noise in the transmitter. Robustness is incorporated in two different aspects, that is, the stochastic errors and the model considering the non-bounded errors. So based on this motivation, we select that why we want to go for physical air security. So conventionally, there are many cryptographic based security techniques. These cryptographic based techniques usually operate on the network layer and above. They have the long keys and the long key generations, and the transceivers that are designed at a physical layer, they are independent of these cryptographic key exchange. So the overall advent, so the major problem in the cryptographic based approaches is that the key exchange is important and the key generation is important. However, with stronger and stronger computational devices coming up, it is highly possible to break the keys, and these cryptographic approaches are becoming vulnerable to the eavesdroppers. So, on contrary, the physical layer security based techniques applies the security techniques at a physical layer. That is, the transceivers which are designed are adopting the security, and they are independent of the key generation and they do not require any key exchange. Furthermore, the utilization of the physical layer security is majorly on the channel characteristics. So what happens is that the idea is the channel characteristics are utilized for the benefit of the legitimate users and while degrading the overall performance for the eavesdroppers. So in this work, I will be utilizing the signal processing methodologies for the physical layer security towards the multiple eavesdroppers. Otherwise, there is also the information theoretic approaches, which utilizes the coding and network coding based techniques to provide the security, but we use the signal processing methods. So the related work in this area is, so most of the physical layer security based methods in literature have been discussed for a simple wiretap setting. This is a setting which considers a single transmitter communicating with a single receiver, and this communication is unicast in the presence of a single eavesdropper. However, there are some instances which consider the multiple nodes, that is multiple receive nodes or the multiple eavesdroppers in the overall communication scenario. So we have the uplink in this paper, and the relay assisted security has been discussed in this, whereas some instances of multicast scenario has also been observed in these papers. The major limitation with this work has been they utilized only the use of the single base station, and the multiple base station has not been addressed in any of these papers. Furthermore, in general, the work which has been studied in literature utilizes only the signal SINR maximizing or the secrecy based approaches or the capacity based approaches. None of the work has considered the SMSE based approaches, which should be the major requirement for mission critical communication, as the mission critical communication focuses on reliability, that is the correctness of the data is of utmost importance, and the capacity and the rate is not primary important. So hence the SMSE based minimization approaches should be considered. We also see the SMSE based secure design in literature, but only for the simple wiretap scenario, that is with single transmitter, single receiver and a single eavesdropper. Hence in this context, there is a gap in the literature, that is the secure designs for mission critical communication has not been reported in literature. Moreover, the secure designs which should satisfy the requirements of mission critical communication, that is a group communication, the multicast communication from multiple base stations, and also the security and robustness is the gap in the literature which we tend to address in this work. So overall, we consider this is a network model where we select multiple base stations. So we propose a multi-base station, multicast communication. That is, there are multiple base stations who are simultaneously transmitting the same message to the legitimate users. So the legitimate users are in green, and the communication is happening in the presence of the eavesdroppers in red, and all the blue are the base stations. So in general, there is a synchronization area, that is this synchronization area is all the base stations that are operating on the same radio frequency channel, and they utilize the same radio frequency the coherence time to communicate, and these base stations would be communicating simultaneously to the group users. So if all the base stations in white communicate together, it is a full MBSFN terminology that is called in mission critical communication. Whereas if the cluster of base station in blue, that is some subset of the entire MBSFN area is communicating, this is a dynamic clustering. So this cluster of base station is communicating towards communicating with the group users is the dynamic clustering. So in this case, we consider a cluster of base station, and we also evaluate the performance which is in contrast to the full MBSFN and other techniques which are proposed for mission critical communication. So in gray, these are the cells outside the MBSFN synchronization area, and these will act as a co-channel interference in the practical communication, which will be utilized for the simulation results. So the way which we select the cluster of the base stations is we do it dynamically. Hence, we utilize the greedy clustering based approach for selection of the base stations. Suppose there were the P base stations in the MBSFN area, and we aim to select KT prime base stations, that is a minimum cluster size that will be communicating with the users simultaneously. So for every user, we select the base station which provides the highest received power. Once we select the base stations, if that number of base stations is satisfying the KT prime requirement, all the base stations would be selected. That is, if the selected base station, that is S, is less than KT prime, we still have to select the remaining base stations to fulfill the KT prime requirement. So hence, if the number of base stations that was selected in the first iterations were higher than KT prime, all the base stations would be selected. If it was lesser than KT prime, we would still need to select the remaining base station, and that selection is based on maximizing the SMSE for all the group users. So the remaining base stations can be selected one by one in this fashion. Hence, finally, the number of the base stations that are selected in a cluster is S. Now, once we select these base stations, let me select the KT base stations in the overall cluster. So our aim is to design the transmitter, the receive filter, and the eavesdropper so as to provide the security in the overall communication. So this is a transceiver model that will be adopted, that we adapted for this work. That is, there are KT base stations that are selected that are communicating to the group of KR legitimate users, and this communication is happening over the channel C between the base station and the legitimate users. This is happening in the presence of the KE eavesdroppers. Let the channel between the transmitter and the eavesdropper be G. So our aim is to design the precoders for each of the transmitter base station, that is V's, and the receive filter R. Here we assume that all the nodes in the communication, that is the transmitter, receiver, and the eavesdroppers, are MIMO equipped, and they can do the beamforming for providing the security. So here, let there be NT number of transmit antennas, NR receive antennas at the legitimate users, and NE receive antennas at the eavesdroppers. Furthermore, we also incorporate artificial noise in the overall design. So the artificial noise component would be added just after the V's. This artificial noise component will be designed jointly along with all these transceive filters, and this is specially added to incorporate the additional security towards the eavesdroppers. So we assume that the eavesdropper is unaware of the artificial noise component, and hence the eavesdropper will not utilize any artificial noise vectors into the overall problem solving. However, the legitimate user is aware of the artificial noise through some feedback, and hence the legitimate user will be benefiting from the security. So based on this design, the signal transmitted from the base station, that is X here, it will be the pre-coded data, that is V times D, plus the artificial noise component that we added, that is W, and Z. Let ZT be the artificial noise vector, and we associate a matrix W that will be the artificial noise shaping matrix. So along with the pre-coders receive filter, we also want to obtain W's optimally for our design problem. Moving on, the data at the legitimate user L can be given by D hat, which will be the receive filter at the legitimate user, the channel on which the data was transmitted from the transmitter to legitimate user, and the pre-coded data, plus there will be the artificial noise component for the legitimate user, and this is the additional noise in the overall communication channel. Based on this, the mean square errors were formulated just by finding the mean square error between the transmitted data, transmitted symbol, and the received symbol at the legitimate user. Similarly, the mean square error can be formulated at the eavesdropper accordingly. So one more thing, that is the eavesdropper would not readily share the information to the base stations with the base stations. Hence, we are unaware of the filter that the eavesdropper would be utilizing. So we consider that the eavesdropper filter is a conventional or a MMSE filter or any linear filter for that matter. And we here in this paper, we consider a conventional minimizing mean square error based filter, straightforward. And finally, we obtain the precoders, receive filters, and artificial noise for our problem. So now the robustness in the overall design is added in terms of the channel state information errors. It is known that the channel state information which is available at the transmitter and the receiver is not always perfect, and multiple errors such as quantization errors, pilot contamination, and estimation errors will affect the overall channel state information that is available. Based on that, the robustness should be incorporated in the overall designs, as the transceivers which were designed by considering the perfect CSI will not optimally work when there were errors in the channel. So for the legitimate users, the channel can be modeled as the estimate that is available, which is erroneous, and that can be added with the errors in the legitimate channel errors. Similarly, at the eavesdropper, the channel assumed is the imperfect CSI, and the imperfect CSI channel information can be modeled as this. Here, there are multiple ways in which we can model these errors. So we assume in this work two types of models. Number one is a stochastic error model, that is where we are aware of the statistical properties, that is the mean and the variance of the errors, and we design a system by assuming the statistical properties. Whereas there is another technique which we opt is non-bounded errors. These are the errors in which these are also called as a bounded region errors, that is the overall error is bounded in some region. Here we assume a spherical region, that is tau, and we said that the norm of this error is less than or equal to some threshold, and these are the radii of the uncertainty region. So it can be modeled as a sphere, and all the errors which are belonging to that sphere can be utilized as the errors in the overall channel. So based on this, the stochastic error based robust optimization problem can be formulated as that we want to minimize the legitimate user mean square error, that is sum over all the users, the mean square error, and we want to obtain the precoders V, the artificial noise shaping matrix W, and the receive filter R for the legitimate user. This is constraint over the mean square error of the eavesdropper, that is the mean square error of the eavesdropper has to satisfy a minimum MSE threshold that is set. This is a design parameter, whereas there is the constraint on the total transmit power at each base station. So based on this, the stochastic error based problem can be formulated like this. Here the MSE for the legitimate users and MSE for the eavesdropper will inherently incorporate the deltas, that is the error terms, and when we are minimizing over all these precoders and transient filters, we are doing the minimization, and we are optimizing over the errors as well. So this is a non-convex problem, and we solve it. And it is difficult to solve. Once we solve it by using the conventional Lagrangian method and utilizing the KKT conditions, we obtain the equations for the desired filters as this. However, still there is a problem, that is all these filters are interdependent on each other. That is, if we see directly the equation for R, it incorporates the precoders, it incorporates the artificial noise, it's dependent on other filters. Similarly, it is the case for artificial noise and also for the V. So it is not possible to directly obtain a closed form solution for such a non-convex problem. However, this problem is still convex in terms of one variable and while keeping the other variables fixed. Based on this, we formulate an iterative algorithm by utilizing the coordinate descent algorithm, wherein we randomly initialize all these filters first, and we try to minimize each of them in each iteration. That is, first we update the receive filter by using the precoders and artificial noise. Once it is done, the next update would be for precoders, and finally for the artificial noise by utilizing the other parameters. Here the Lagrangian variables deltas are obtained such that it minimizes the constraint for the eavesdropper MSE and for the transmit power respectively. So these are the Lagrangian associated with each of the constraint respectively for all the transmitters. So this iterative algorithm is trying to optimize the overall optimization problem, that is objective, and obtain the filters in an iterative sense. And hence the solution which will be resultant from this will be overall optimal solution for the desired filters, which are robust and also secure towards the stochastic errors. However, for the non-bounded errors case, that is when we are unaware of the statistical properties and the overall error is bounded in a sphere. So along with the two constraints which we consider for the statistical errors, that is C1 and C2 was the MSE for the eavesdropper, the power constraint for each of the transmitting base station, and C3 and C4 will be the additional constraint for the non-bounded errors. That is, these are the bounds of the errors that are selected in the region. So here delta belonging to GE, where GE was the definition that we selected the errors from the region, and C4 were for the legitimate users, similarly belonging to Cs. So based on this, an equivalent optimization, now this optimization problem can be, these constraints can be considered as infinite solutions, because there are multiple possible deltas and they are continuous, and that can be selected from the overall sphere. So this can be considered as infinite solution. So the way we tackle this problem is by using the worst case approach. That is, we reformulate this overall problem as a worst case problem, and we try to eliminate these we try to merge these constraints with the respective terms. That is, we have minimizing over the filters while maximizing the legitimate users MSE. So once we formulate it as a min-max problem, the delta TLs get associated with epsilon L, and similarly delta TE get associated with the minimization of the MSE for the eavesdropper that should satisfy a required threshold of gamma. So this problem can be reformulated like this. Now this again is a non-convex problem, and the solution is not straightforward. So here we separate and we decompose this overall problem into three subproblems. That is, one is minimization, the other is maximization of the legitimate, and the third one is over the eavesdroppers. So we can reformulate the overall problem into three subproblems. That is, we want to minimize over the desired precoder, receive filter, and artificial noise. We want to minimize the desired MSE for the legitimate users while satisfying the C1 and C2, which were the MSE of the eavesdropper and the power constraint. The first problem, that is here, is similar to the already solved stochastic error-based problem. Solution to this problem is straightforward as directly adapted from the first stochastic error-based problem, which we have already seen. This next problem will be the minimization over the deltas, that is the error terms, and it is reformulated from the maximization problem, hence the term negative, on the epsilon L. Here the desired constraint will be only for the legitimate user. So this is by assuming that we are already aware of we already have the solution to optimal transceivers, and we are also aware of the worst case error for delta TE, and we solve for delta TL. Similarly, once we know delta TL and we know the transceivers, we can form the problem for delta TEs, that is for the eavesdroppers. So the problem can be formulated as this. After solving it and approximating the solutions, we obtain the equations for the errors for legitimate user and errors for the eavesdroppers as this. Again, as the solution to each of the problem was not straightforward and close form solution, we develop an iterative algorithm which solves three problems one by one iteratively. That is, we solve the first problem and obtain the transceivers by assuming that we know the channel errors. Next is, knowing that we know the transceiver and the legitimate user channels, we obtain the eavesdroppers. And similarly, we finally update for the legitimate users channels. Hence, once we solve this iteratively and we try to minimize the mean square error of the overall legitimate users at each iteration, we obtain the desired robust and secured filters, and also quantify the norms, the channel errors in the non-bounded error-based problem.
Deepa, can
Yes.
I ask one question?
This is
Yes,
Sanket.
sure.
Yeah, so in the previous algorithm, means I understand that you are optimizing these precoder matrices for these transmitter and receivers. But I see that this KT is the parameter that decides which base station should coordinate together, right?
Yes.
So is this algorithm based on condition on, like, after you choose a set of base stations that will coordinate? and then you perform the optimization over the pre-coding matrices for those base stations? Or is it a joint process that you do the simultaneous grouping of the base stations and as well as this optimization together?
No, Sanket, that is also one possible solution of doing the simultaneous, but we, however, do it like first the base stations are selected, and those will be the transmitting base station for a coherence time. So once that is selected, we do the optimization of the desired transceivers and also the channel errors. But after every coherence time, we again select the best base stations and we do it again.
I see.
So if it solves,
So
yeah.
if these two processes are separate, then the selection of the base stations, if I understood correctly, is to maximize the received SINR, right? I
Yes,
mean, so the sum
yes,
SINR.
yes.
Then the calculation of those sum SINR, does it consider the channel estimation errors, or how does it? Because
Yes,
I see that the optimization happens later based on the
yes.
model of the channel estimation errors. But when the selection of the base station is done, then how should one calculate the sum SINR?
So the first step is utilizing the best base stations or selecting the best base station, and the best base station selection is only based on the available channel knowledge. Here we assume whatever is available channel knowledge, and we obtain the base station which will maximize the SINR or give the best performance for all the users, for some or all the users. The other option is uh, the other technique was utilizing the errors, but we do not consider it because we only can function based on the available channel knowledge, and we can design a transceivers that can overcome the problems in the estimate that is available to us. So here we do not consider the errors in the design while selecting the base stations. We only make our
Okay.
transceivers robust afterwards.
Okay. Okay.
But yes, that is possible, and that's a good way. Maybe we should incorporate. Yes,
Okay. Thank you.
thank you. Yes, so once the base stations are selected, this process is done, and this is done. This stays static for a coherence time, and after that time, we again reselect the base stations and do this uh, optimization again for the desired need. So we here are the numerical results for the proposed design. The two aspects which we proposed were the robustness and the security. So this is the plot for the bit error rate versus the SNR, where we compare the robust and the non-robust designs. So the robust design are in two ways. That is, here we represent NR as a non-robust design. Robust was as per the stochastical error, that is represented as RSE, and non-bounded error is RNBE. So it is observed that the non-robust design performs the worst as compared to the other robust designs. Whereas knowing the knowledge, here the red curve represent the stochastical errors and the green represent the non-bounded errors. So it is observed that having the good statistical knowledge of the errors in the channel is a good advantage over when we are not aware of the exact error properties. So the non-bounded error performs in between the non-robust and the stochastic error-based design. However, it is still observed that we observe a 3 dB drop as compared to the non-robust. Hence, the reliability is improved, and also whereas the stochastical errors observes almost a 6 dB drop as lower SNR. So hence, it is always good to have a robust design over non-robust design to improve the overall performance of the system. Furthermore, if we see the effect of these errors on the mean square error versus SNR, and we vary the error variance or the we vary the error variance. So it is observed that as the error variance is increasing, that is from 0.25 to 0.4, as the error is increasing, the channel properties are degrading. Hence, the overall performance also degrades. So furthermore, the perfect system, that is was assuming the perfect CSI knowledge, performs the best of all the cases, and it will be a lower limit, that is the bound which we always want to reach. So here we again compare the stochastical error, non-bounded errors, and non-bounded errors and the non-robust design. And it is again demonstrating the similar performance, that is non-bounded error falls in between the stochastical errors and non-robust design. So hence we conclude that knowing the good statistical properties of the errors is a advantage, and the non-bounded errors is a trade-off between the stochastical errors and non-robust. However, it still should be considered to provide the robustness, as it still enhances the performance as compared to the non-robust design. Furthermore, in aspect of security, we analyze the security gap performance for the three different designs, comparing the three different designs, that is non-robust, robust non-bounded errors, and robust stochastic errors. So in this, the security gap is the performance parameter, which is the difference in the SNR for the legitimate and for the eavesdropper. So for example, we set a threshold on the minimum requirement for the legitimate user, that is, we want the bit error rate always better than 0.10 raised to minus 4, suppose that is a requirement in our case. And the maximum for the eavesdropper, here we consider that the eavesdropper should always be about 0.3, which is a very poor bit error rate in order to for the eavesdropper, so that they cannot decode the signal. So once we set these thresholds, we observe the SNR ranges and the gap between these thresholds, and this gap provides a quantitative property on the advantage of the secure and reliable region. So the secure and reliable region is the one wherever I will be satisfying the required bit error rate for the legitimate user, it's always a reliable region, and the security is below the for the eavesdropper. So this is a trade-off between this is a gap that quantifies the secure and reliable region. So the lower the gap between this SNR, the better is the advantage, and the overlapping gaps, the overlapping regions, is the best case which we can observe. So here we see that the gap is reducing for robust non-bounded errors as compared to non-robust, and for stochastic error we observe an overlapping gap, that is, there is a huge region which is providing both the secure and reliable communication. So the stochastic error based design provides the best performance, and good security is observed between the bit error rate for the legitimate and for the eavesdropper, and good overlap is observed for the stochastic errors. Yes, so the gap here is roughly around 4 dB, and here it was observed to be 2, whereas here it's minus 2 for the thresholds, which was set as 10 raised to minus 4 for the legitimate users and 0.3 for the eavesdroppers. Finally, the physical layer performance for the bit error rate versus the SNR, demonstrating the bit error rate for the legitimate and the eavesdropper, is presented while varying the component of artificial noise in the overall system. So it is observed that the bit error rate for the legitimate is very low as compared to the eavesdropper. So here the red curve demonstrate without artificial noise, whereas others are with the artificial noise. So it is observed that by including the artificial noise, as some power was dedicated while the design of the artificial noise, the performance of the bit error rate deteriorates uh, by including the artificial noise in the system. However, the difference is not too much, and this can be considered. But for the eavesdropper, the addition of the artificial noise is providing a huge advantage. In this case, if we see at a higher SNR, the advantage with and without artificial noise is huge. So incorporating the artificial noise will definitely give the benefit over the security towards the legitimate eavesdroppers. This is also, here we do not see a clear distinction for the eavesdropper, but this effect is better understood if we see the MSE threshold requirement for the eavesdropper. That is, we want to observe the mean square error threshold that we set for with and without the artificial noise in the system. It is observed that without artificial noise, the higher MSEs, that is beyond 0.7, if we set the MSE threshold for the eavesdropper beyond 0.7, these higher thresholds are not satisfied for with artificial noise based design. So this is the requirement. This is the threshold that is set, that is for 0.8 and 0.7. So this is the curve should always be about this. But if we see without artificial noise, beyond 0.6 or roughly beyond 0.7, the thresholds are not satisfied, whereas all the thresholds, even the very high strong thresholds, are satisfied for the case when we incorporate the artificial noise into the system. And the more the artificial noise, the better the secrecy, as we can see the difference between blue and the green curves. So artificial noise is a strong component that is providing the security towards the eavesdroppers. Finally, we also observe the overall performance for the system level simulations. That is, we consider the MBSFN area. As I discussed, the MBSFN is the overall participating base stations in the synchronization area. So if all the base stations were communicating simultaneously, it is the MBSFN. Whereas if each base station was serving independently on its own radio frequency resources, it is the SCPTM. These are the terminologies that are set by 3GPP and ITU for the mission critical communication standards. So if we utilize a cluster of base station which is falling in between MBSF and SCPT, it is a dynamic clustering. So we observe this, we compare these three different systems for a secured and robust design, and we observe the outage probability over the bit error rate thresholds. So the first curve is for the legitimate users, and this is the bit error rate for the eavesdropper, the B1. Here it is observed that more and more number of users are satisfying the requirement for MBSFN, and the outage probability is better for MBSFN as compared to the SCPTM in red, and these are the dynamic clusters with the dynamic cluster size as 5 and 10. So it is observed that MBSFN is sending the messages by more and more number of base stations. The maximum number of base stations here were 20. So if more base stations are transmitting the same symbol, the recovery of the symbol will be better for the legitimate users. So this is a benefit of utilizing the MBSFN over the SCPTM, and it will provide the reliable communication, whereas the dynamic clustering falls in between the two schemes. However, Utilization of multiple base station is also the advantage for the eavesdropper, as eavesdropper can also recover multiple copies, will receive the multiple copies of signal and hence try to decode better. So these eavesdropper will also follow the similar trend, that is MBSFN is performing the best as compared to SCPTM and dynamic falls in between. But the difference between the legitimate curves and the eavesdropper is huge, which is providing the overall security, and this was obtained by performing proper beamforming and adding the artificial noise in the system. Hence, the dynamic clustering or MSFN can be considered for the mission critical communication to offer the best reliability and the secure system. So, in conclusion, I would try to say that we designed an efficient multi-base station communicating by the multiple transmitters, multi-antenna, secure MIMO transceiver design that meets the reliability and security constraints of requirements of the mission critical communication. So mission critical communication for public safety or critical infrastructure is a relatively unexplored topic, and the transceiver designs in particular for mission critical communication has not been reported yet. Furthermore, they deserve the specific designs because of the unique and joint requirements, that is the security, reliability, coverage and multicast services should be offered simultaneously, and the designs should be able to satisfy all the constraints simultaneously, and they are for the critical infrastructure. So traditional designs focusing on the capacity or the rate maximization problem or the some secrecy rate maximization, they no longer apply, and the SMSE based techniques should be adapted for better reliability. In future work, we aim to detect the eavesdroppers by better learning algorithms and provide the security towards overall mission critical communication in terms of active eavesdroppers, that is when they can also alter or jam or spoof the overall communication. Yes, so these are the relevant related publications for this work. Thank you. Any questions?
Deepa, so are there some questions in the audience?
Yes, please.
Perhaps I have a question. Well, I'm wondering about the, if I take an information theoretic viewpoint, whether the scheme that you use for the analysis makes assumptions, and whether, for instance, the eavesdroppers, if the eavesdroppers would use another decoding scheme, and use other information theoretic assumptions, could do better than what you have in your setting. It's a rather general question, but I'm just wondering about the formulation of this type of channels with eavesdroppers may be made quite general, and whether the assumptions that you took for assessing the bit error rate, or the in a sense the capacity of the channel and the conditions looked
Yes, the information theoretic
specific.
Yes, the information theoretic.
And so yes, my question is whether please.
No, sorry, I interrupted. Sorry.
No. Yes, I was wondering whether the framework that you developed is general enough to guarantee that the eavesdropper, if the eavesdroppers would use another information theoretic framework, could do better than what you assess. That's the general question.
Yes, thank you, sir. I think the information theoretic approaches are providing good coding based codes to provide the security, and that's one more aspect of physical layer security. So the physical layer security has been addressed in terms of information theoretic or the using the signal processing techniques. However, the literature is still limited for both the scenarios, and information theoretic aspects also have been studied mostly for the simple wiretap communication. And to my knowledge, with such a complex scenarios, that is with multiple antennas and everything is so complex, the design of the codes will be complex enough. But I do not have a good expertise in this information theoretic. Yes, I have studied little, but only for literature, but I do not know if they can perform better than the signal processing. But yes, they are also equivalently providing good security. There are many codes which are discussed in literature.
So what is new in terms of information theoretic problem is that you have several transmitters which in a sense collaborate to transmit to also a set of legitimate receivers, and this is in a sense yes, this is a very general problem in terms of information theory because of this many to many situation, right? That's your and so what you say, if I get it correctly, is that the capacity of this equivalent of the channel with eavesdroppers was not studied in this generality.
It is not.
Okay.
It is not in general to multiple nodes and multiple passive eavesdroppers. Yes, it is. I have not found that. Yes.
Mm-hmm. And if you simply, sorry, please.
And also the requirement was here more majorly for reliable communication. So in general, what was studied so far was only the capacity based approaches or the secrecy rate optimization based approaches for the signal processing. But that is not a requirement for a mission critical infrastructure. So this is the another motivation which should be considering the reliability along with the security.
Okay. Thank you for the complete answer. Thanks.
Thank you.
I have one question, Deepa.
Yes,
That
sure,
means
Sanket.
I'm trying to understand one of the bullets point in your conclusions that the traditional performance metrics such as the rate maximization or the capacity are not relevant with mission critical communications, if I understood correctly. But I
Yes.
was wondering, like, for example, when you say capacity, do you mean by just the simple Shannon capacity, or is it the secrecy capacity or the secrecy rate that the users achieve?
It is a secrecy rate. Secrecy rate, that is the rate between the legitimate users, difference of the rate between legitimate users and the set rate for the eavesdropper. That is secrecy rate which I was referring to.
Okay, but I
That
was wondering, like, when you say mission critical, usually now it matters also how much data you're, means I understand that the reliability and security are of paramount importance. But on the other hand, if you say, like, I have some amount of data to communicate, but if I cannot communicate that with enough speed or the within a time frame of, let's say, latency or something like that, but let's talk about the rate and then within the time limit, then wouldn't that be like, means in my opinion, honest opinion, I feel that the rate, secrecy rate should also be an important aspect of mission critical communication apart from reliability and security, because if you cannot deliver secure information within a time frame, then even though you have reliable or the secure information, probably it will not be a timely information, or like the
yes,
information will
yes.
not be reached to the users in timely manner.
Yes, Sanket, that is true. The latency is also important, but mission critical communications are dedicated with special channels, so they are not overcrowded. Plus, only the group users, which are legitimate users, and which are the part of the overall group in mission critical communication, are serving. So it is not overcrowded. So that is the reason we mean that. the rate is not very important because the channel is good enough to serve that many users, and that is a special dedicated channel at 700 megahertz for mission critical communication. So the main problem here was only focusing on the reliable communication to reach there. But latency, yes, if we utilize, the latency is important, but it is possible to utilize the overall channel for and obtain the good rate of transmission, because it is not shared with the commercial users, it's not overcrowded, and it has a good available channel for mission critical communication.
Okay, thank you.
Other questions? Apparently no other questions. So thank you again, Deepa, for your presentation.